Hello, my name's Chris Kurzik, and I'm the principal engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
We're going to continue our work with PTB4 and look at example 4.32, internal design pressure, conical shell. In this example, it's without a transition knuckle and it's centered axis. There's a few different types of conical type shell connections. And so we're going to review the simplest one and probably the most commonly found. We're going to begin with ASME Section 8 Division 1, and then we're going to continue on to the what ASME allows for the code case under 2695. So let's begin with ASME Boiler Pressure Vessel Code Section 8 Division 1. Okay, so we're back. So we're looking at Section 8 Division 1 in our first example. We're looking at a conical shell, no transition knuckle. The dimensions are shown here. We've got a length of 78 inches. And I've put here something interesting. I've added this to the example as a supplement. This is the large end length of the cylinder on both sides. So it's 36 on the small end and the large end. There's a deviation from the example because I wanted to sort of describe a little bit, touch on the extra reinforcement required. And then we have our corrosion allowance down below. A post-weld heat treatment, no, in this example, weld efficiency. And we have our pressures and temperatures stated. So now we're ready to continue. So let's just go back and take a look at UG32 and just look at the spec. So formed head sections and pressure on a concave side. So what we have here is some definitions of the dimensions. L is for large, S is for small, and ASME uses those pretty universally. And there's a definition section, and the L and alpha. So there's some restrictions, of course, on how much alpha can be. And then the one on the right side is talking about if it's off not concentric. So when it's concentric, alpha 1 will be equal to alpha 2. But basically what they're saying, and this is in section 8 division 1 and 2, they're saying if you have an off-center axis, then you take the maximum of alpha 1 or alpha 2, which makes sense because you're looking at the most severe case. And this is designing by rules. So, there's a limitation on what you can do, but basically that's the approach with design by rules. So we're going to look at UG32 formed heads. And we're going to look at part F. It says conical heads and sections without transition knuckle. So the required thickness of a conical heads or conical shell sections shall have a half angle of alpha not greater than 30 degrees. So that's one of the rules that you have to follow. And there's two different ways to solve it. You can solve it in terms of the thickness and get your nominal thickness, the left side equation, and then what we typically do is then we solve it and then we put it back into P, and we find out what the final P is, and then and then we look at the whole chain and we figure out where the limiting pressure or the limiting component is. So there's also a reinforcing ring shall be required when required by 1,5D and E. And in our example, the example given by ASME, they don't really touch on it, but I'm going to touch on it a little bit in this this presentation. The conical heads and sections having a half angle of greater than this without a transition knuckle shall follow equations 4, 1, and 5G and 1, 5G. So, the rule of thumb is, don't exceed that, but if you have to, you can follow those rules. But I typically steer away from them unless the client asks for it. So preliminary calculations. So we're just doing the setup, the allowable stresses. We got that from UG 23 section 8, section 2D, and we get the allowable stresses, and then we determined the final pressure, and we make the adjustment for the hydraulic head in the vessel, and then we take some adjustments for the corrosion allowance, and then we calculate with that the tan angle. In this case, we've got a concentric one, but if you had, an eccentric one, you do that equation twice and you find your maximum. So in this case, we have 21 and a very precise angle, and this is just show you that this matches the example exactly. So that's how we basically do it. So then method 1, division 1, we have an angle less than 30 degrees. Okay, so that's the first check. So that means that if we can follow UG32G, if we have an angle less than that, we calculate that with that equation there. We put in the cos angle, and it's very similar to the conical one except for the cos and the alpha, and we get 1.448 inches, and we take the corrosion allowance and we get 1.573. In this particular example, we're not using the closest nominal, but you certainly can. And we will continue the next slide. Next thing we do, the second check we do, is we check for reinforcement. This is in addition to the example, by the way. And so we just do a quick check to see whether reinforcement is required. And first thing we do is we check the minimum length, because the shell on the large end and the small end have to be long enough, and we use that equation. It's just slightly different for the larger one. The larger one requires more straight length of the shell. We call that we had 36 inches and we're at 21, so we have enough length there where we can use the other equation. So then the next one is we can calculate the delta, and it's the same on the large side and the small side, and we get 43.57 degrees by putting in the pressure and the stress on the shell side. And I mean, most cases your shell and your cone should be all the same materials. Most fabricators would use that, but it does discriminate, so do that. And then the first equation, it says, because delta is less than we do the first check, so delta is less than alpha, and we say, of course not, it's not, so reinforcement is not required. But in this case, the second case, we do the equation and we come up with delta of 11.35 degrees. And of course, the answer in this case is yes, so reinforcement's required. And perhaps due to lack of time, we can go through that in another episode, talking about how to do the reinforcement calculation. Basically, the approach is to one, either increase the thickness so that you get enough reinforcing area, and secondly is to install a stiffening ring. Okay, so let's jump into the second, the division 2 calculation that's shown in the example. And basically, we calculate that, using a very similar equation as before, and we determined the thickness to be 1.571, and in this case, I took the nominal thickness of 1.625, and then we're basically done with this. So let's compare them. Okay, so let's look at the comparison. So you can see from division 1 and 2 that the thicknesses are almost identical. And the difference being is if you took the allowable stresses in division 2, you would definitely do see a much thinner part.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.